Welcome to the presentation of our brief announcement, Communication Efficient Weighted Reservoir Sampling from Fully Distributed Data Streams at SPAA 2020. Our goal is to popularize fully decentralized distributed streaming algorithms. The predominant model in the literature is the continuous monitoring model illustrated here on the left. The workers receive distributed input, meaning that each worker gets some of the items, but they communicate exclusively with a distinguished coordinator node. This node is responsible for computing and providing the entire output. Clearly, in an actual implementation, the coordinator's communication interface will be the bottleneck. In contrast, we use a fully decentralized model illustrated on the right, where in addition to the input, the computation and output are also distributed. There is no distinguished node, and communication is between the workers. Furthermore, we don't synchronize on every item. Not only is that not the granularity that users typically want, they want the system to ingest lots of items and update the result quickly, for example, every second, but not for every item. It's also practically infeasible and unnecessarily complicates algorithm design. Instead, the input is presented in the form of mini batches that the algorithm ingests, updating the result, and then proceeds with the next mini batch. Such a model is widely used in practice, for example in Apache Spark streaming mode, where a mini batch could, for example, be the items that arrived over the last second. However, algorithms research rarely uses such models, and we ask ourselves why and hope that this will change in the future. To showcase that this model is useful, we apply it to the problem of weighted reservoir sampling. The task is to maintain a weighted sample without replacement over the entire input seen so far, with new items arriving all the time. The definition of weighted sample without replacement is that for some sample position and some item that's not already in the sample, the probability of that item being in that sample position is its weight divided by the weights of all the items that aren't already in a previous sample position. To the best of our knowledge, there's only one other rather recent paper that studies distributed weighted reservoir sampling published at PODS last year. However, it uses the centralized continuous monitoring model from the last slide, and that results in quite a bit of unnecessary algorithmic complexity. The way our algorithm works is to adapt a sequential algorithm of Ephraimides and Spirakis, which assigns keys to the items which are basically exponential random variates with the item weight as parameter. Then, the k items with the smallest keys form the desired sample. And because we proceed in mini batches, we maintain a threshold that's required for a new item to enter the reservoir, and that's simply the kth smallest key at the end of the previous mini batch. Here you can see a schematic view of the data flow. Because the algorithm is fully distributed, every processor maintains a local reservoir. At the top, new items come into the system, get their keys assigned, and those larger than the threshold are immediately discarded. The rest are candidates which we insert into the local reservoirs. At the end of each batch, we perform a global selection for the kth smallest key, which becomes the threshold for the next mini batch. And then we discard all items with larger keys, and the result is the sample that we wanted. This is repeated for the next mini batch, and so on. Now, clearly the step that requires the most consideration here is the selection. In the previous paper, we showed that selection from locally sorted items can be done much more efficiently than the classic unsorted selection problem. But here we need to dynamically insert items a lot. The solution is to use a search tree to represent the local reservoir. Then we can easily insert items, and we can also augment search trees to support rank and select queries efficiently, as well as splitting them at some arbitrary position to discard the newly disqualified items quickly. And this completes the basic algorithm. Now let's look at some measurements. What you see here is a weak scaling experiment on up to 256 nodes of 4HLR2, an HPC system at our university. On the left side, each processor, which is a CPU core here, gets 1 million items per mini batch, and on the right it gets 10 times fewer, so 100,000. In the plots, we compare it to a centralized algorithm that proceeds very much in the same way as ours, but gathers the new candidates at the coordinator node, where it performs selection and maintains the result. It still operates in a mini-batch model though, of course. Our algorithm is marked with solid lines and filled marks, while the centralized algorithm has dashed lines and hollow marks. We performed these experiments with 3 different sample sizes, namely 1,000, 10,000, and 100,000 items. Note that these are all pretty small sample sizes, but they're big enough to make our point. The centralized algorithm scales much worse. In fact, there's only one configuration where it does better than our algorithm: small batches and small samples. When the sample size grows, it becomes terribly slow and achieves really bad speedups. See the green lines at the bottom for a sample size of 100,000 items. And it also doesn't benefit from larger batch sizes nearly as much as our algorithm does. So, in contrast, our algorithm's running time barely changes as the sample size increases. In conclusion, we've seen good scaling for our fully decentralized algorithm and much worse scaling for the centralized competitor. Even on a few hundred nodes, the centralized algorithm just can't keep up. And we hope that others in the field of streaming algorithms will consider fully decentralized models too. We think that the distributed mini-batch model is ideal for this because it's realistic, easy to work with, and useful, in fact used, in practice. Thanks very much for sticking through to the end, and we're looking forward to your questions in the live discussion on Wednesday.